All right there, class. How are we doing today? We are here to deal with, continue our discussion on vectors and scalars. And specifically today, the objective is to understand how vectors add using drawing methods. Now, just a recap, we've talked about this in a previous video, but we have two kind of classes of quantities that we deal with. One of those is something called a scalar, which has magnitude only, and a vector having both the magnitude and direction. Now, since we're talking about vectors here, what we're going to deal with here is mainly just, let's talk about the vector part of this. Now, since a vector has a direction, a convenient way to draw a vector is using an arrow. So let me pull in some vectors here, and basically, the one thing that we can say about all these vectors that you see here on the screen is that they all point in the same direction. So my question to you is this: because they point in the same direction, are these the same vector? So I want you to go ahead and stop the video. I want you to think about the question that I just asked. Are these the same vector? So here we are, we're back. One thing I hope you can see from this, that even though they're all pointing in the same direction, these are in fact not the same vector because the magnitude is what's different here. This one has a larger magnitude. Now again, by magnitude here we're talking about size. So if I line these up, well, we can clearly see that these vectors are not the same in size. Probably this green one and this orange one here, they could be potentially the same vector as well. There's a little bit more to it that goes into that, but that's the basic idea. In order for a vector to be equal, it has to have both the same magnitude and the same direction. Okay, so what we want to look at here is how do we actually add vectors together. So let's take a look at an example here. Let's imagine we have two vectors here. Let's propose that this one right here is, let's say, 3 meters east, and we have this one here which is 4 meters east as well. Now our goal is to take these two things and add them together. Basically the way I would do this is I'd take these two, you put them next to one another like this, and the answer of the sum of these two is what we call the resultant. And I'm going to use the red arrow here to indicate that. Now if we go 4 meters east here, and then an additional 3 meters east here, the resultant is the 7 meters east. So now the question is, what happens if instead of the 4 meters east and 3 meters east, what if we change this around a little bit? Let's suppose we have, we'll do the 4 meters east again, but this time what we're going to do is we're going to take and we're going to rotate this so that it is not 3 meters east, but it's actually 3 meters to the west. So let me just change this around here. And of course we're dealing with west. So get rid of this. And there we go. So difference here, of course, is the fact that instead of going both in the same direction, they're actually opposing directions. So basically what I'm going to do here is I'm going to actually take these two things, I'm going to put them, if you can imagine walking from this side here to over, you walk from the start to here, and then somebody walks back this way. You can see that from our beginning, we're starting here, but we actually end up in this location. So in a sense, what we're doing here is we are actually ending up, and let me just copy this out here. What we're actually doing is we're starting in this location. Instead of adding to the end, it's almost like a subtraction problem. What we're doing here is we're ending up with our resultant right here is actually this 4 meters east and the 3 meters west, it's kind of like taking 4 minus 3, and what we end up with is a 1 meter to the east. Now let's suppose, let's change this around a little bit again, and instead of the 4 meters east, 3 meters east, or 4 meters east, 3 meters west, let's suppose we go 4 meters east, and here's my 3 meters. Let's suppose we rotate this so that instead what we're going to do is actually go 3 meters to the north. So basically we start here, we walk down along this line, and we turn and walk 3 meters to the north. Now hopefully it's clear to you that you can't just take 4 meters plus 3 meters, because the distance between the start and the end is not going to be 7. And I hope it's also clear that we can't take 4 meters and 3 meters and subtract them, kind of like we did here in the second thing. So basically what this comes down to is we have to deal with the shape that this makes. In this case, the shape that this makes is actually a triangle. Let me see if I can drag this triangle up here. So I've just redrawn this here. If we look at the resultant of these two, we'll see that it starts here, it ends there. And this, I hope, is very clear to you, is not 7 meters. It's not 1 meter. It's going to be some other thing in between that. To actually find this mathematically, we would actually have to do the Pythagorean Theorem, because east and north are going to make this right down here a 90-degree triangle, or the 90-degree angle in this 90-degree triangle, and therefore to find this third side we would have to do the Pythagorean Theorem. So just to recap, when we deal with vectors, we can add them in if these are what we call collinear. They share the same line. It's basically like an adding problem or subtraction problem. When we put together vectors that are at right angles together, we're not going to be able to just do a simple adding or subtracting. We actually have to do some kind of Pythagorean theorem or some other method with that requires a little bit higher level mathematics. That's not a part of this video. That's a video later that it will take care of.